And so we'll start talking more about bond polarity. And simply what I mean by that is, from what we learned of the carbonyl, that's delta minus, the carbon's delta plus, and how that can guide us into making specific types of bonds as we look at things that are really complex. So if you're familiar with, the rules of the game, which are the reactions, how can we learn to sequence them? And so really we call this functional group transformations. So FGT, and that's really what today is all about. An acid to an ester, an acid to an amide. It's keeping the oxidation state the same, but changing one part. And we've seen so far about protecting groups. When we have these issues of reagents that can act upon two different functional groups, how do we limit that? So here really is the remainder of this module. Your book draws this much prettier than I have, but it's called a starburst scheme. And the center of the star is the carboxylic acid here. And for purposes of this talk, I've just used butanoic acid. But again, really where we're focusing our attention on is, this part of the molecule where ultimately what we're doing is changing what is bonded to the carbonyl group. And in terms of the key or the map here, in green is where you typically see the carbonyl shift. And then red, the approximation of the sp2 hybridized carbon in the carbon NMR. So what do I want to do first? The way I present it here and the way we talk through it might be a little different, but a carboxylic acid is a good starting point because they're easy to make, and we'll see some reviews and some new ways of doing that. One issue with them is if you want to substitute out OH for something else, OH is a bad leaving group. So probably the most common thing to do first is to make an acid chloride. And so the name there, you can see a little bit with the nomenclature. It's called butanoyl chloride, so you have NOYL, then a space, and chloride. These are special from the IR because that carbonyl stretch is always at 1800 for an acid chloride. And the carbonyl carbon shifts a little bit, 10 ppm. So really, the IR is probably more diagnostic for these functional group transformations than the carbon shifts are. But once you make that, the chlorine is a really good leaving group. So you can make any other derivative from that. And so going off to the top right, if we were to treat that acid chloride with methylamine, this is a condensation. If you see what's lost, you're losing HCl. So an H from the amine and the Cl from the acid chloride. So a condensation that forms an amide. So amides have a carbonyl shift less than 1700. And again, that's due to the resonance. So amide bonds look more like this, where you have a sort of more CN double bond character than CO double bond. And so that makes that carbonyl weaker, so it drops below 1700. And this is a secondary amide because the nitrogen has two carbonyl substituents. You can make a tertiary amide if you were going to use dimethylamine now, so HNMe2. And so this is now tertiary because you have 1, 2, 3 carbons. And then to make a primary amide, you basically have to start with ammonia. So that makes just 1 bond to carbon. And so acid to acid chloride to amide, where the nucleophile you use is an amine. And if we focus our eye here on the primary amide, of all of the classes, only that one can be dehydrated. So if you look, you're losing the elements of H2 and then O. And that's going to form a nitrile. So again, it's still at oxidation state 3. But that will get you into that. And so notice the chemical or the IR stretch of that is 2260. That was region 2. So the triple bond stretch. So that's sort of a walk around from an acid to a nitrile. One reaction that we'll look at today is starting from the acid going straight up to the ester. It's called a Fischer esterification. And so notice now the H of the acid has been substituted for a carbon chain. So that's 2 carbons, that's named first, followed by a space, and then these end in OATE, so ethyl butanoate. So once you form an ester, you can then treat it under basic conditions, which is called saponification. And that ends up with now a sodium or whatever salt, metal salt. So sodium butanoate. And then there's a slide about why that's useful. If you've ever seen Fight Club, they do some organic chemistry in Fight Club, and we'll talk about that. If you treat the acid directly with, say, sodium hydroxide and water, that will form the sodium salt. And then finally, another condensation or dehydration is when you take 2 equivalents of an acid, you can dehydrate it to form an anhydride. And so the anhydride in the IR, again, that was the one that always had 2 carbonyl shifts, so that's pretty diagnostic. And so with that preview, what we'll do today is look at the reaction conditions that carry this out. And then sort of as a preview for Module 4, once we know how to make all these things, we really focus then on the chemistry of the alpha carbon. So again, that has special acidity, and then we use that to examine a new set of reactions. So kind of the same flow. We'll go through the functional group, how you name it, what the physical properties are, how you know it's in there using IR and NMR. So the carboxylic acid, again, has CO2H, and that carbon must always be at the terminal end of the chain to be in that form. And so the R1 is any other group attached to the acid. So as we see in the nomenclature using from the carbon count here, you take the parent carbon chain, you drop the E, you replace it with OIC and then the word acid. So methane becomes methanoic acid. If we're using sort of common names, it's also called formic acid. And if you take your socks and shoes off and roll around in the grass, eventually some ants will bite you. And the sting that you feel is they're injecting formic acid into that bite. And so if you've ever been bitten by fire ants, one's okay, but when it starts getting more than that, it's a bit much. So ethane is ethanoic acid, and this is acetic acid. So that's what's present in vinegar. So if you're, like cleaning your bathroom or your tub or whatever, vinegar is a good thing to use. That helps clean it. It's also in Italian dressing. That's the sort of zing. So, you can, formic acid I wouldn't eat, but maybe acetic acid's fine. So you see the trend, propanoic, butanoic, pentanoic, and then the last one is benzoic acid. So if you treat that with sodium hydroxide in water, you end up with the sodium salt. So that's called sodium benzoate. And I bet if you look at your can of Monster, there's sodium benzoate in there as a preservative. It's a pretty common thing that's added to food as a preservative. One thing I want to point out is really the boiling point. You see they're all pretty high. And I'll draw a structure on a slide coming up of why that is. The carboxylic acid is both a hydrogen bond donor and acceptor, and so that really bumps up the boiling points as compared to the alcohol of the same carbon count. So if you've ever smelled like pure acetic acid, I mean, you kind of can imagine what vinegar smells like. So pure acetic acid is just like that on steroids. As you get to 3, 4, and 5 count, they start smelling worse. I mean, they smell pretty pungent. Benzoic acid probably doesn't really have a smell too much because it's a solid at room temperature. So as I mentioned, so I'll just draw it R1. So there's your carboxylic acid. And what these things tend to do is hydrogen bond really in the form of a dimer, where the OH is a donor and then the carbonyl is an acceptor. So we would say that carbonyl is accepting that OH. It's going to look kind of weird, but draw that the other way. So there's a H bond, donor, acceptor, and then you have another one that's crudely drawn. And that dimerization is why the IR looks the way it does, why it's different from alcohols, as we'll see on the slide coming up. But that non-covalent interaction, since these are attracted to one another, that's why the boiling point increases. You have to break all those little interactions. And as we mentioned, compared to the same carbon count, acids will typically have a higher boiling point than the corresponding alcohol. So how do we know that you have that acid functional group in there? The IR is probably the most indicative. So your OH stretch looks pretty unique, coupled again with the carbonyl. The carbonyl carbon, again, that will be in the 180 to 200 range, depending on what is bonded to the sp2 hybridized carbon. So really what your eye is focused on here is this really broad region there in region 1. And then you have the carbonyl stretch in region 3. So just to refresh your memory, see how this OH comes down? It doesn't go back up like an alcohol does. So it's merged in with all your normal CH stretching. So maybe I'll draw it in blue. If you had butanol, the OH in butanol would go down like that and then come back up before going back down again. So IR really is the best way to determine that. Another important difference about the OH group in an acid versus an alcohol, even though they're both OH, the acid's pKa is 5, and so that is 10 to the 10 times more acidic than an alcohol. And so as we learned in Organic 1, the reason for that is that negative charge of the conjugate base is delocalized through resonance. So for the acid, again, say we're just using hydroxide as the base. That negative charge can go on to the other oxygen, and so that stabilizes it. Whereas if you deprotonate the alcohol, the negative charge just stays on the one oxygen. And so that's one reason you can invoke to explain this really big difference in acidity. So remember that the pKa is a log scale, so that's why it's 10 to the 10. So these two examples, ethanoic acid versus ethanol, you can see that here you have an sp3 hybridized carbon, there's sp2, and so that can undergo the resonance hybrid formation. Don't think we need to belabor that anymore. So one thing that does affect acidity is the stuff that's bonded to the alpha carbon. What we want to keep in mind, again, just draw it in the middle here. So every acid, as I said, has that CO2H, so that's the functional group. Your starting point is always a pKa of about 5, no matter what. But how does that change? How does it become more acidic? And in the series you see down here to the very right, here was acetic acid. And so the pKa is about 5. And what is happening in this series is a hydrogen atom is being substituted for a more electronegative element. So here's fluorine. So we know that's delta minus due to electronegativity. That's going to make the alpha carbon delta plus. And essentially what's happening is I'll highlight it in blue here. So there's your OH bond. That fluorine is tugging through the sigma bonds because it's electronegative. So the more of those heteroatoms that you add, you can see it's increasingly dropping the acidity. So you add 2, now it drops it to pK of 1.4. And then when you get to trifluoroacetic acid, it's now in the negative. So trifluoroacetic acid, if we just approximate, it's about 10 to the 5 times more acidic. It's a pretty common reagent. It smells more potent than acetic acid. It will wake you up for sure. It's almost like if you're going to go bench 250 or whatever in the gym, it will wake you up. I mean, it's pretty pungent. So that's an example of induction. Again, when the through bond description of things is induction. That's, again, totally different from resonance. Resonance has its own sort of rules to follow. Now, in this series, we've extended out the carbon chain. So there's alpha, beta, gamma, delta. And what we're doing is looking at the number of bonds between the H and the F. So we start off the alpha and then we move it all the way to the gamma. Unfortunately, I don't have the actual pK values for this. But essentially, by the time you get to the last one on the right here, when fluorine is at the delta position, that's essentially the same pKa as acetic acid. The tug of war effect, the farther you move away, the lesser it is. So, if you're in tug of war, if you're at the end of the rope, you're not really doing much work if there's like 20 people in front of you, right? So if you're right in the middle of the action, you're feeling that pull the most, and that sort of helps conceptualize this concept as well. So that was a little bit about acidity. And over the next couple of slides, what we'll do is look at how do we make carboxylic acids, knowing the stuff that we learned already. And we'll first look at that in the context of carbon dioxide, so CO2. And the question is asking you, how would you categorize, according to hybridization of the carbon, its oxidation state, and then its reactivity? So if we draw out the Lewis structure, that's carbon dioxide. So it's a linear molecule. The carbon atom has 2 sigma bonds, 2 pi bonds. So it has to be sp hybridized. That eliminates A. If you count the oxidation state, you have 4 bonds to oxygen. So that eliminates D. And so 4 is the highest oxidation state. And chemically what that tells us is this has to, it has to act as an electrophile because the oxidation state can only drop down. And so that eliminates B, and we're left with C. So we know that the carboxylic acid is at oxidation state 3. And what we're going to learn is that that carbon of carbon dioxide can be transformed into the acid carbon of a carboxylic acid. So geometry we said was linear. So here are some reactions that we learned in passing, and then on the next slide we'll draw out some reactions and the mechanisms of them. So a carboxylic acid can be synthesized from CO2. Again, that's the terminal carbon. And then a Grignard reagent is the rest of the chain, whatever that may be. Alternatively, you can use the nitrile CN group as an equivalent of CO2. So these react, as I said initially today, with different polarities. So carbon dioxide is an electrophile. And then a metal cyanide, sodium, potassium, lithium cyanide, whatever. The cyanide is a nucleophile. So we'll talk about polarity and how these methods complement one another, and maybe what's good and what's bad about each of these methods. With the nitriles, that's essentially what you're doing is SN2 chemistry. So let's draw some of this out so we can visualize what we mean by what's happening. We'll just keep to what we started with, so that's butanoic acid. So that arrow means retrosynthesis. That's what we want to make. And then what do we make it from? So in blue, I said we want that carbon to come from CO2. So that means we want to make this bond, which I'm drawing a dotted line through. And if the blue carbon is coming from CO2, that means the other 3 carbons have to come from a nucleophile. So 1, 2, 3. We want a carbon nucleophile at the end with some metal balancing it out, N+. And then carbon dioxide plus an organometallic. So carbon minus, how did we learn how to make those? So we could start with, say, bromopropane. And then we learned that if we treat that with, say, magnesium metal and diethyl ether, so that makes the Grignard reagent. So the strategy is that from that initial carbon, which is delta plus, by treating it with magnesium, now the carbon's minus, so the polarity has inverted. So once we have that, I'll just draw it like this, minus MgBr plus delta minus. The negative of that carbon is attracted to the positive of that carbon. And so the arrow will flow that way. And then we break a CO pi bond. So that's, again, a nucleophilic addition. So at that point, we have the carbon in the chain, but we're not done yet because we have to adjust the pH. So typically, we would add aqueous HCl. So in general, even though the pK of the carboxylic acid is 5, you want the pH to go below that so that you're ensuring that you've really pushed it to the acid species and you don't have any of the salt left over. So again, it's pretty general. You know, if this was another example, that would be like 3-methylbutanoic acid. You identify the alpha carbon, and the acid part comes from CO2, and the rest of the molecule comes from a Grignard reagent. So on the next slide, we'll show a complementary method where the polarity of the reagents is reversed. The carbon that ends up being the acid will come from a nitrile. So we'll keep the same butanoic acid. There's our alpha carbon. The dotted line is what the bond we want to make. So in the reverse direction, we need 3 carbons and then a leaving group. And then the acid carbon will come from potassium cyanide. So again, because that's at oxidation state 3. You can do an SN2 reaction. And now you're not quite there because you're left with a nitrile, but the nitrile can be hydrolyzed. So you need pretty strong acid, water, and then usually the boiling point of water. So you're heating it pretty hot. So that will hydrolyze the nitrile to the acid. So pros for potassium cyanide, it's a solid. Cons, you really have to be careful handling it. I mean, it's a white solid. As long as you're safe, it's pretty easy to work with, but you don't want any acids around because that generates HCN. Pros for CO2. It's, again, when I say CO2, the easiest thing to use is just dry ice. You can use CO2 gas, but then you're bubbling things, and that can be a challenge. So it's cheap, it's a solid. Cons, normally you're using a huge excess. And what I mean by that is you don't typically weigh it. You just get a block of CO2, you smash it with a hammer to get little pebbles, and you just chuck it in. And so it's fine if there's excess because it just bubbles out when it's done anyway. For potassium cyanide, you're pretty much you're weighing it out in a 1-to-1 molar ratio. So that's two methods of getting the carbon of the acid into the molecule, where it's, just write another thing here, polarity. So here it's an electrophile, and then KCN, it's a nucleophile. A couple other things that we studied this semester were oxidation reactions. A primary alcohol with chromic acid, that was the Jones oxidation. You can also use potassium permanganate. Again, these require water as part of the mechanism. And what we saw most recently, an aldehyde plus MCPBA also goes to a carboxylic acid. One reaction from last semester. If you have an alkene as a restriction, at least one of the sp2 hybridized carbons has to have hydrogen. So a fully tetrasubstituted alkene won't do this. An alkene plus ozone gas, and then an oxidative workup, so like hydrogen peroxide. That will do an ozonolytic cleavage of the double bond. So what you would get in this case is 2 equivalents of acetic acid. And conceptually what you're looking for is the alkene, you split it in half, and then each carbon then becomes an acid. If both carbons of the sp2 hybridized center there, if these were both carbons, you'd end up with a ketone. So that's a restriction for that condition. So once we've made the acid or the acid chloride, what is outlined on this slide, what I want to draw your eye to is, see this X group here? And then in blue, I'll show the nucleophile up here. These oxidation state 3 functional groups undergo a mechanism that's called nucleophilic acyl substitution, or NAS. And that mechanism is 2 mechanisms you've seen. it's a nucleophile adding, and then the X group is being eliminated. So addition, elimination. The carbon at oxidation state 3 is sp2 hybridized. The nucleophile attacks it. The pi bond is broken. The carbon is now sp3 hybridized. But what is different now, X is usually a heteroatom, right? So it's gone from oxidation state 3 to 2, and X is a good leaving group. So the carbonyl reforms, eliminating off that original X group. And it's been substituted by the nucleophile. So overall, it's called nucleophilic acyl substitution. So just to highlight or track these things, there's X, it has left. Then in blue, the nucleophile is now added and it's substituted where X was. So of all the oxidation state 3 groups we learned, these follow sort of a trend in how you get them to react. And it depends on what the X group is. I guess before I get to that, we'll do this transformation and then we'll generalize it according to what X is. So the first reaction here is pretty classic. It's called a Fischer esterification. And so you can take any carboxylic acid with any alcohol. Under acid catalyzed conditions, it will make an ester. So again, this is the same Fischer that proved the structure of glucose and did a lot of other things, but maybe what I'll highlight in red. So there's the OH, and maybe I'll use blue. See the alcohol here, ethanol. So that oxygen of the alcohol plus the carbon chain, that is what ends up in the molecule. And then the rest of it, highlighted in green, nothing changes there. So really when you're looking at like an ester, the bond that you would dissect is this one here. So everything over here comes from the alcohol. Everything to the left comes from the acid that you started with. So you notice there's an acid catalyst. Sulfuric acid's pretty common. Your reagent and solvent are the same thing. And then you really have to heat these pretty high, again, because it's equilibrium. And on the next slide, I'll show you the mechanism of what the acid is in there for, and then how the alcohol substitutes the OH group. So under that arrow, I wrote equilibrium. All the mechanistic arrows I'll show will be the back and forth arrows. And then when we're done, I'll tell you how you control the equilibrium to end up with only product in there. So HA is sulfuric acid. I'm just going to represent A as sort of the rest of that. So A minus will be the sulfate conjugate base. So if that's an acid, if sulfuric acid is the stronger acid, the carbonyl gets protonated. The ethanol itself can get protonated, but again, acid-base reactions are pretty fast. So even if it is protonated, it gets deprotonated just as fast, and nothing productive happens when it is protonated. So once we've formed that, we can draw a resonance form that will help guide us. Where the carbon is now plus. And so now that is an electrophile. The alcohol is the nucleophile that attacks it. And so, again, because we're under acidic conditions, we cannot form O minus. The oxygens always have to be either neutral or positively charged. So I'm going to draw out all the proton transfers here. Just keep in mind that it'll get kind of steppy because we just have to keep moving that proton around. So we need to lose the proton from that oxygen. And so that regenerates the catalyst. And now all of that's neutral. Now one of those other OH groups, the oxygen has to be protonated because we got to get an oxygen out of the molecule. So it gets protonated. And now, so we're almost there. We're going to use that other OH group to do an elimination. So that's going to push water out. We end up with the carbonyl protonated. That conjugate base, which will then abstract that proton. And so that regenerates the acid catalyst HA. And it forms the ester. So, as I said, it's equilibrium. So if you want to control the equilibrium, you can do a couple things. As I wrote above the arrow there, you can use a huge excess of the alcohol so that all of the carboxylic acid is fully consumed. And then, as I said initially, the difference between an alcohol and an acid is the boiling point, right? So if the alcohol boils out lower, you can distill that out and be left with your product in the flask. The other thing you can do if your alcohol is pretty expensive is you can remove the water that's formed, because that will shift the equilibrium as well. So there's ways of doing this, but you can put in a solid drying agent that will soak up the water. You can get fancier as well if you do organic research. There's an apparatus called the Dean Stark trap where you distill your stuff up, then there's a second arm. The water flows into that. Because there's a difference in density, it settles below. So it's pretty neat to watch if it works smooth. Most of the time, you really have to heat these things quite a bit to get that water out of the reaction. But that's a pretty classical mechanism. And again, since I said it's equilibrium, if you wanted to go the other way, take an ester to an acid, instead of using an alcohol, you would now run this reaction in water. So your ester plus water plus acid, it just follows the reverse mechanism back this way. So just, again, keep in mind that's what those arrows mean. It's like if you're on a trail, if you go out to the Longleaf Trace, there's a couple little trails. You can follow the trail one way. You're sort of following it this way. But, you can go back the other way just as fine. That's essentially what that means. So we got about 20 minutes left. So if this has biological implications, but I'm just showing it for a small molecule here, ethyl propionate. The reaction that's shown is called saponification. And this is under basic conditions. So an ester plus sodium hydroxide will form this salt. You can isolate the salt, or if you adjust the pH with HCl, you can re-isolate the acid. And so what's the first rule of Fight Club? We don't talk about Fight Club. So if you look, do you know what he's holding there? Do you know what they did with that soap? Well, the soap is what they were using to make money to fund Project Mayhem. But they were making the soap from fat. And if you've seen the movie, it's where they get the fat is a little bit gruesome. But what I mean by fat is, see this part of the ester? That's just a really long chain, like 12, 14, 16, 18 carbons long. And this alcohol, it's sort of one oxygen, right? But if you go into biochem, like lipids, which are fats, are glycerols, like triacylglycerol. So basically what that is that triol. And so you can imagine off each of those alcohols, you have that fatty chain. And so that's pretty common in biological systems. So as you learn more about molecular biology, you'll see that lipids make up cell membranes. How does it work? I think the chains point into each other and the polar things are on the outside and the inside. So that lipid bilayer is what the cell is. I don't know, if you think of like a basketball or something, that's the surface, right? So that keeps the outside out and the inside in. So that's organic chemistry, that's how a cell is, the structure of a cell. But what they were doing was basically taking fat from liposuction, like women that were getting liposuction, they were taking human fat and then saponifying it to make soap. And then they were selling that soap back to them in like a boutique where they thought it was fancy. So, I mean, it's interesting if you understand sort of how gruesome it was. But that, I don't know if you guys will do it in 256, but when I was a TA, they did saponification to make, and when you touch it, I mean, it feels slippery like soap. So, and I think you take like just beef fat or something. It's not too hard to do. But that's like human evolution, right? So this is like when you think about how this came into being and people cooking and then figuring stuff out. So that is the Fischer esterification and then saponification back to the salts and then adjusting pH. Those are pretty standard reactions. So since the saponification was basic, let's just talk about the arrow pushing for that so we can look at the charges involved. So in this case, hydroxide is a nucleophile. So keep that in mind, even though we say sodium hydroxide is a base. Because it's not doing a proton transfer here, it's a nucleophile. Carbonyl is delta minus, carbon's delta plus, so that attacks. And then we break the pi bond. So notice the carbonyl now is not protonated. So under basic conditions, it'll be negative. So these mechanisms tend to be a little bit easier in the sense that there's not a whole lot of proton transfers going on. So we collapse and then we eject out now the alcohol part, so ethoxide. And so we form the acid, but since we formed this, which is a good base, it will deprotonate. And so these arrows are all one way. It's again not an equilibrium as in before. So I think I want to write ethanol here. So that is the saponification under basic conditions where the oxygens are negative. Again, the salt you can isolate. Like I said, sodium benzoate's a common food additive. These things are pretty stable. If you wanted to adjust the pH, you could do that as well, but for the most part, I don't know the exact physical states, but this is probably like a solid salt, which means you can it'll precipitate and you can filter it. If you adjust the pH to the acid, that acid is probably a liquid, and then it's a little harder to get out of the reaction. So when you're getting your 43% yield in lab and you're like, it says, what are some things that went wrong or whatever? If you avoid the cheap excuses like, I didn't weigh it out right, or I spilled it. It's probably a solubility issue for the most part. It's like, okay, my stuff is stuck in the aqueous phase. How do I get it out? So that tends to be what I and students in my lab deal with a lot is, okay, it's in one of these flasks somewhere. So we'll finish today with the reactivity profile of what that X group was. So we're talking about R, carbonyl, and then X, where X is your leaving group. And the way that this slide can be explained is that you can only use certain leaving groups to get these reactions to occur. And the logic of it is based on pKa. That's ultimately what it comes back to. So again, think of these things as your starting material. That's the bond you're trying to break, and then substituting that thing out. So in acid chloride, the leaving group is Cl minus. The conjugate acid of that is HCl, and the pK of HCl is -7. For an anhydride, the leaving group is a carboxylate. Its conjugate acid is a carboxylic acid. And then we said those pKa's were 5. So you see right there that jump from negative to positive. And then as you analyze the other ones, the leaving group for an ester is an alkoxide. Its conjugate acid is an alcohol. That's a pK of 16. The amide leaving group is coincidentally called an amide. Its conjugate acid is an amine, and that pK is 38. So really the hard line is I'll draw it thicker right here. Acid chlorides are the best substrates to start with. Anhydrides are okay. The reason you would not want to use an anhydride is, see this whole thing leaving? It's producing another molecule that you just have to separate. For the acid chloride, it's just producing that. And that will typically, be water soluble, so it washes out in the aqueous phase. So a lot of these reactions start with acid chlorides to substitute that for something else to make an ester, an amide, whatever we want to do. Skip that. And so here is our template of what nucleophile will react with an acid chloride to form the new product and what that name of that is. So if we think of it as this, if we have an acid chloride with water, that will make a carboxylic acid. An alcohol makes an ester. Ammonia makes a primary amide. Primary amine makes a secondary amide. Secondary amine makes a tertiary amide. Thiol makes thiol ester. We'll see a little bit in module 4. When nature does this, nature uses thioesters to do these sort of substitutions. We don't really use it in lab. They're more reactive, and plus working with thiols really smells bad, like really bad. And azides make acyl azides. So we learned how to make carboxylic acids, but how do we make the acid chlorides from them? So typically it's always acid to acid chloride and then whatever other nucleophile to make your desired product. The one that we'll talk about with the rest of our time here is a reagent called thionyl chloride, which is pretty common. What I tended to use in lab are these second conditions. We probably won't talk about that too much in class, but these are much more mild conditions that are just easier to work with. Thionyl chloride has a smell to it, and the byproducts are pretty corrosive. So if there's any like metal around, because these reactions produce gas, the metal will immediately like rust and turn green and corrode. So there's pluses and minuses to these things, but for our intent and purposes, here's an example of thionyl chloride. So that's shown here, SOCl2. And some people call this like lasso chemistry. But again, the OH is being substituted for chlorine. And then once you have that, then you can treat with your other nucleophile to make an ester, an amide, whatever you're trying to make. So if you started with 3-methylbutanoic acid, really all you would do is cool it in an ice bath and then pour in thionyl chloride. You'd probably start at 0 degrees, but you could start at room temperature, and the reaction is exothermic enough that the heat it produces makes the reaction go forward to completion. And within an hour or two, these are done. Typically what you can do is stick a balloon on the flask and watch the balloon fill up. And then you periodically empty it, and then when it stops filling up, you know that the reaction's done. So how does that happen? So if you look at that sulfur, everything in there is a heteroatom, but they're all bonded to sulfur. So sulfur is kind of unhappy. It has 2 chlorines tugging on it, double bond to oxygen, so it's electrophilic. And I'm going to show this maybe in a weird way. So that will drop down to form a double bond, and then this double bond will actually attack that sulfur. And then we're going to break the weakest bond there, which is the pi bond. So there's a pretty famous chemist at Texas A&M named Dan Singleton. He wrote on Twitter, 4 or more arrows. So if you draw 4 or more arrows in a arrow pushing mechanism, that's a conspiracy. So we've drawn 3. We're not quite in conspiracy territory here. Once you start drawing too many of these curved arrows at once, then it's debatable about that's actually happening. What we're trying to do is make the OH into a good leaving group. And I've drawn it sort of in a roundabout way, but I wanted to show that being protonated. So you can see the sulfur is still pretty unhappy. So the oxygen drops down and a chlorine is displaced. So we can have that chlorine attack that. We might go a minute or two over here. Sorry about that. So the resonance shows us that chlorine attacks that carbon. Now we have the carbon in there. And what we'll do now is that OH, we're going to push those electrons from that oxygen. Push it down like that. It's going to form a pi bond. We then break that O sigma bond. And then we can show that chlorine leaving. So I know that's impinging upon 4, but so that loses SO2 gas. That's what's corrosive. You form Cl minus. That does the proton transfer, and that gets you your acid chloride. So a little bit different mechanism than what we're used to seeing, but really what you need to know is an acid plus thionyl chloride gives you the acid chloride. And what we'll continue on Wednesday is, once we've formed that, how do we react it with nucleophiles to make the other oxidation state 3 functional groups.